Hello, my name is Hayden McKay, and I'm going to explain to you a little bit today about how fast does current travel, the actual speed that current travels at. Before we do that, I'd like to sort of talk about how we measure current. And current is the amount of charge per unit of time. So we're measuring how much charge goes through a wire in a given amount of time, and that allows us to measure the current. So if you have a lot of current, a little amount of time, or a lot of charge in a little amount of time, it's a big current. But if you have that same amount of charge in a shorter amount or a longer amount of time, then we're going to have a much smaller current. Now, how do we actually measure how that current moves through and at what speed it moves through those electrons passing the charge down the line? Well, we can think about it a little bit like a water slide. As you have here, if you can see, the water, one drop of water goes in, and we're not measuring how long it takes that drop of water to get to the very bottom of the water slide. Instead, we're measuring how long does it take for this drop of water to feel the force of that drop of water. Think about it, this thing is all full of water, so you put one drop in, it's going to force one drop out very, very quickly. And that is the actual speed at which we're talking about. But the electrons themselves don't actually move that fast. They move at a speed we like to call drift velocity. So as these electrons are in the metal is held together very tightly, where these electrons can bump into each other and they can kind of move around almost as if it were a fluid. And these electrons move at this drift velocity. Well, let's say we had a copper wire here that had a cross-sectional area of 3 times 10 to the negative 6 meters squared and about a 10 amp current moving through it. That would yield a drift velocity of only 2.5 times 10 to the negative 4th meters per second, a few millimeters in a second. That drift velocity is only a meter, an hour. So if that were the correct logic, then we would say, okay, I turn on my vacuum cleaner and it takes an hour for it to go through that cord and then turn on. But we know that's not the case. So there's something else happening. Well, that's the actual speed at which the electrons are moving through. They act as sort of a chain reaction. You can think of this as like a bunch of people standing in line. You've got a bunch of people standing in line and someone gets impatient in the back and pushes the person in front of them. That force is felt, right? Each person pushes on the next person, moving forward, and the person in the front then gets pushed forward. But the person in the back didn't actually go all the way to the front. We're not measuring how long it takes for the person in the back to get to the front, because in reality that person only moved a short distance. That sort of is, drift velocity. The people in line, they only moved an inch in a matter of however long that took. But the force from the back to the front was felt very quickly. And that's the speed. And that is often 100 million kilometers an hour, almost instantaneously. A little slower than the speed of light, but still almost instantaneous. That'll, as you open the circuit, turn on your light, turn on your vacuum cleaner, turn on whatever you're turning on, that electric field gets passed through all these electrons that are within the metal, that are moving around and able to kind of feel each other's force. They feel it almost instantaneously. It shoots down the wire, and just like this, the current up here moves very quickly and is felt down the other end. So that's a little bit about how fast current moves and some of the misconceptions that come with it.